Okay, we are live. It is 3:30, and for all of you on watching this on YouTube on a different day, this is hat day today. I don't always wear a. Thank you. No, I don't always wear a hat. All right, so welcome. This presentation today is about, or no, you're supposed to grab it from the, see, I don't even wear hats, okay. Is about structural design. The last presentation we gave was more about logistics, and which we'll probably have another follow-up presentation on that. But this one, due to popular demand, structural design, going into depth about the soil mechanics of the footprint of our project, of our West Tower project. And with me, we have Amy Dean from MKA, Magnuson Klemensic Associates, and also Doug Lindquist from Haley and Aldrich, the geotechnical engineer. Both firms are top shelf, very well known throughout the Seattle area. So, and also in the room, we have Methune Architects, and also we have Andersen Construction. Great. All right. So, yeah, let's just get started. This is Doug Lindquist. The other one is Amy.
Thank you. It's a pleasure to be here. My company starts each meeting with a safety moment. My company starts each meeting with a safety moment, so I thought we'd do that right here. And what to do in the event of an earthquake. What you should do is you should drop, cover, and then hold on. So maybe find a table or something like that that you can get under if there's a seismic event, and then wait it out. You do not want to run out the front of the building because things sometimes fall off the fronts of buildings. So with that, let's get on to our presentation. So we'll do introductions. There's a lot of initials after my name and Amy's name, and I just thought I'd share with you what those are. PE stands for Professional Engineer. It's a license in the state of Washington. The GE is a licensed geotechnical engineer, which I am in California. The state of Washington doesn't have that quite yet. Amy has SE, which is structural engineer, and then lead AP is leadership in energy and environmental design, accredited professional. So I'm a local person. I grew up a little south of Seattle, went to the University of Washington for my bachelor's and master's. Then I got active in public organizations related to my field, becoming a president of the Seattle Section Geotechnical Group of ASCE, which is the American Society of Civil Engineers. Then I joined the ASCE 61 Code Committee for the seismic design of piers and wharves. Then got active in the Earthquake Engineering Research Institute, becoming a board member of the state chapter of that. And then, because I work so closely with the structural engineers like Amy, I wanted to better understand and speak their language, so I joined the Structural Engineering Association of Washington and got involved in their Earthquake Engineering Committee and had the opportunity to go to Japan after the March 2011 earthquake and tsunami in Japan. And that was actually like 14 years ago this month that we were in Japan observing the damage from that earthquake. And we have the very similar hazard, as many of you are aware, off our coast of Washington as to what the type of earthquake that occurred in Japan at that time. And one of the highlights of my career was speaking at my master's thesis advisors symposium in honor of him. He literally wrote the book on geotechnical earthquake engineering. And another highlight of my career is being here with you all today. So thank you.
Hello, as Eli and Doug said, I'm Amy Dean. I will give you a little background on myself. I have my bachelor's degree from Vanderbilt University in Tennessee. I'm actually from Oregon, but decided to go, thank you, farther away for college. I have my master's degree from the University of California, Berkeley. Go Bears! I've been at Magnuson Klemensic Associates, MKA. Yeah, sorry. I have been at MKA for 19 years. I'm a principal in the residential and hospitality group, meaning that most of the work I do is on condos, apartments, and hotels. In my time, I've worked on over 60 projects, including 10 peer review projects, which we'll is what the West Tower will be and what we'll talk about a little bit more, and 25 residential towers. As Eli noted, MK is very active here in the Seattle area. We're based actually here in Seattle, just at Rainier Square. And here are just a handful of Seattle-based projects that are ones that we worked on as structural engineers. So the Amazon Spheres, the new convention center and the old convention center, the Century project at the Space Needle Lumen Field, the Overlook Walk, and the new aquarium that just opened earlier this year. I'm gonna pass it on to Doug, who will talk about Haley and Aldrich's work.
Sure, thank you. For some of you who are in the construction business, you may have heard of the company Hart Krauser, and that's the company I worked with for the first 22 years of my career, and then they were purchased by Haley and Aldrich 5 years ago. And so I'm referring to all the projects just as Haley and Aldrich projects. But these are a number of the projects I've worked on. I worked on some of the ones Amy mentioned as well. The one on the top left is the 4th and Madison Tower. Here we had to retain a building on two sides with the excavation going adjacent to it. We're going to try out this mic instead. I'm seeing some positive signs there. So for this site, we had to excavate on two sides. Our project for Horizon House, we're just doing the excavation on one side. I also worked on the Century project with MKA and the Husky Stadium, Go Dogs, where we remodeled that, I want to say 10 or 15 years ago. And all three of those first projects I worked on with MKA. The project on the far right is the SR-99 launch portal for the Bertha tunnel boring machine. And then the viaduct, which has now been removed, is shown in the top right of that image. So my company was brought in because of our deep excavation design experience and seismic design experience, and are the engineer of record for that largest bored tunnel in the world. Another world-class project here in Seattle is the SR-520 floating bridge at roughly 1.5 miles long. It's the longest floating bridge in the world, and we were brought in to design the anchors that are at the bottom of Lake Washington. And my company has also worked on all of the aircraft carrier piers in Puget Sound. There's 3 of them, and Pier B at Puget Sound Naval Shipyard, shown in the bottom. And one of my favorite projects that I did early in my career, that's a large mechanically stabilized earth wall, the tallest wall of its type in the Western Hemisphere. It essentially has steel reinforcing strips going back into the soil, and then concrete facing panels holding the soil in place. It's 135 feet tall and was part of 13 million cubic yards of soil that came in for the construction of the third runway in the early 2000s at the SeaTac airport. So let's talk a little bit about the history of tall buildings in Seattle. Seattle has a really rich history dating back to 1914 when the Smith Tower was constructed at over 462 feet tall. So an amazing civil engineering feat put on by the engineers of that time frame. That was a mere 63 years after the Denny Party settled in West Seattle in 1851. So an incredible feat there. And that was the tallest building west of the Mississippi until the Space Needle was constructed for the 1962 World's Fair. Unfortunately, I didn't work on that, but I did get to work on the Century project where we evaluated the Space Needle as part of the recent upgrades. So next, I want to focus on the right-hand side where we show and have a number of buildings constructed after the World's Fair in Seattle. So if we zoom in there, I've identified some of the kind of outlier buildings, those tallest buildings in their era. It includes the Columbia Center, 1201 3rd Avenue, US Bank Center, 4th and Madison, Russell Investment, F5, and Rainier Square Tower. And what you see is Haley and Aldrich and MK's logos are all over those buildings that we've worked, both firms have worked on the majority of those really signature towers in the Seattle area. So there was a question to Horizon House about hiring an established geoengineering company to work on the Horizon House Tower, and I'd say you have very qualified geotechnical and structural engineering companies working on this building. What's interesting is the tower building is cyclical. So there were a bunch of buildings in the 70s and 80s, and then there were no towers for 12 years, from 91 until 2002. Part of that was the recession of the early 1990s, and then the dot-com bust, and also just overbuilding of the downtown core in the 80s. After that, we had a series or a period of buildings. Then we had the Great Recession, and because when you start a building, it takes multiple years to actually get it finally built, there's a bit of a lag between when you start and end. And so after a building boom, there was the Great Recession from 2007 until 9 that caused there to be another period of no buildings being constructed. And then after that, we have a period that I call the smile period, where a company that sells books on the internet decided to found their headquarters here in Seattle, and there was a large demand for a lot of office and apartments to support the growth of the city. And it was an incredible growth boom, which was really neat to see, this being my home city. What that looked like in 2017, this is a picture showing where the tower cranes were. And many of you probably remember this, but Seattle had more tower cranes than any other city in in the United States. More than Chicago, 2 or 3 times as many as New York, twice as many as Los Angeles. Just an incredible growth for a relatively small city compared to these other cities. Then 2 years later, there's a comment in here that says Seattle has the most cranes in the country for a 3rd year in a row. This is incredible amount of growth for what was a relatively small city. So again, 59 cranes at that time, twice as many as Chicago and New York, a 1/3 more than Los Angeles, twice as many as Portland and San Francisco. So there's been, and Amy and my firm being headquartered here, we all got to work on a number of high-rise buildings during this time frame. So let's now move into the Horizon House project. That's a little bit of a background, 2 tall buildings, and for the most part, we're focusing on the seismic design of the new West Tower. So this is a cartoon I kind of like about a developer in Pisa who wants to save some money to avoid taking some soil tests, and the Horizon House didn't do this. We've had the chance to do a number of soil tests out at this site, and that's the first thing we do when we start a project. First we go and look and see what existing information is available, and then we supplement that with collecting additional soil information. Another big part of it is earthquake engineering. That's a large portion of the presentation today. Other geotechnical elements include the earth retention, shoring, or supportive excavation. That's what you see when you drive around downtown Seattle and there's a big hole in the ground and there's a vertical cut right next to the city sidewalk and streets. That's what I'm talking about there. Then obviously you need a foundation for the tower, and it's important to put that on the appropriate soils. And then as you're coming back up, that supportive excavation is usually temporary, and so we have foundation walls. So we provide recommendations for Amy's team to design those foundation walls, as well as the foundation. And then during construction, the geotechnical engineer is on site to observe the soil conditions, make sure they're consistent with what we expected when we did the explorations and in our design. And then we also are monitoring nearby buildings, the supportive excavation, and other elements. So these are a couple pictures that were taken during our exploration program, showing the drilling rigs, and we collect samples every 2.5 to 5 feet vertically during the exploration program at discrete locations. I know this is kind of a tiny picture, but it's a satellite image illustrating the site. The site's bounded by roughly where I'm showing the cursor, and all the black dots are existing explorations from before we started this project, and the blue dots are the new explorations that we performed as part of this project. And I forgot to mention this in my intro, but I also worked on the North Tower at Horizon House, so I'm thrilled to be able to be involved in this project as well.
I'd like to just check in. Is everybody seeing the dots all right? Maybe not. So there are, I'll come up here. There are 1, 2, 3, 4, 5, 6, 7, 8 blue dots, and the blue dots indicate.
Those are new explorations for this project.
Right. And then the black, where were the previous?
There's a black dot where the cursor is.
Yep.
Here, 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 over here,
Yep.
up here, down here. So another half a dozen or so.
This line in the middle, what is that line for? The one that's indicating E1 zone?
That
and
was
E2?
a distinction that we used in our design recommendations. So those are cross sections, if you will.
Mm-hmm.
And actually, my next slide, I do want to show you a subsurface cross-section.
Right. So to summarize, we already, before this project began, there was already some historic record from prior borings of the soil types that the West Tower, of the West Tower region. And since then, we have bored an additional, how many? 7, yeah, it was an additional 7 borings just to reinforce our
Understanding of the subsurface conditions.
Mm-hmm.
Yep. Thank you, Eli.
You're welcome.
So we're going to zoom in. This is section A prime, A on the left downhill side, A prime up on the right-hand side to the east. So I'm going to zoom into that cross-section. And what you can see is, if you can't read it from where you're standing, but the existing West Tower extends from here to here. So this white space kind of in the middle and these steps are part of the existing West Tower. And what we're going to do is we're going to follow this dash line down through here, and we're going to essentially dig out a little bit deeper to install a larger new West Tower in this footprint. And there was a question about any archaeological artifacts or things like that we could come across during the excavation, and that's always a possibility, but I would say given the previous activities and construction at this site and how it's already been dug out some, that it's less likely to occur here than at a site that hasn't had that prior development and buildings on top of the soil. So we have 4 different soil layers. We have a green layer up at the top that's kind of a fill type of soil. You wouldn't really want to put the foundation on that. Then we have this, I'll call it light tan or yellowish tan, that is a nice sand and gravel. Below that, we get into a clay and silt, and the yellowish and this clay silt are both glacially over-consolidated, that the glaciers have compressed those materials, so they're good for supporting new vertical loads. And then the lowest layer is very deep. That's a very dense sand and gravel. So you can see that the building foundation is intended to be on these more competent materials at depth as opposed to the greener soil up near the ground surface.
So when we hear the word bedrock, where is bedrock in this image?
Bedrock is about 3 to 4 miles below the ground surface in Seattle. So there was a question about that, about, hey, can we put this building on bedrock? And none of the buildings of this type, and including the 850-foot tall project that Amy and I's firms worked on, are bearing on bedrock. They're bearing on glacially over-consolidated soils. We had 2,000 feet of ice compressing all these soils, and that's much heavier than any new building that we're going to put on them. So this is a favorite cartoon of mine. It's Calvin and Hobbes. Calvin's asking his dad, how do they know the load limit on bridges, Dad? And Dad says, well, they drive bigger and bigger trucks over the bridge until it breaks. Then they weigh the last truck and rebuild the bridge. And Calvin says, oh, I should have guessed. And the wife says, dear, if you don't know the answer, just tell him. So this is an example of performance-based design. And you're going to hear the performance-based design quite a bit in this presentation. But this is not how we go about doing it. This is an expensive and risky way of going about performance-based design. So instead, we use computer simulations to do our performance-based design, and especially the performance-based seismic design that we're talking about today. So as part of that, we start out with the geotechnical engineer performing what's called a probabilistic seismic hazard analysis. And I'm going to share that some of the things I talk about and that Amy talks about are rather technical in nature, but I've been told that you are a very well-educated audience and that you're lifetime learners, so hopefully you don't mind hearing some new things and are open to this. But in this probabilistic seismic hazard analysis, what we do is we take a look at all the possible earthquake scenarios that we think are reasonable, and so that includes big events off the coast and shallow crustal things nearby, and we assign the likelihood that they occur or how frequently they occur, and then we also look at, if that occurs, what will the damage be or the amount of shaking at our building site. And so when we do that, oftentimes people ask me, what magnitude is my building designed for? Magnitude 5, 6, 7, 8, 9, and my response is that it's designed for all of them, because we are considering the full suite of earthquakes that could occur at the site. We also know that there's some earthquakes that we just don't know about, and so we've assigned some probability of an earthquake occurring on a fault nearby that we just don't know about yet. And we've tried to do that in a logical manner. So once we know what the hazard is, we select and scale ground motions, and we've given Amy and her team 22 ground motion pairs. So those are orthogonal ground motions, 2 horizontal components for her to put as input into her performance-based model and design model of the West Tower. And then all of this work that we do is peer-reviewed by, usually from California, experts in earthquake engineering, structural engineering, and geotechnical engineering and seismology. And those experts are retained by the city of Seattle. So they have no vested interest in this project going forward. They could shut it down if they didn't agree with the recommendations that we're putting forward. And so there was another question about, are there any shortcuts or difficult decisions we had to make in the design process to save money or something like that. And really, there's not the opportunity to do that. We need to meet the standard of practice and the codes and procedures, and it's reviewed by experts from out of town, usually, who are very experienced with that. The city could potentially do this themselves, but they feel that they want really the top people in the industry to do it, and that's why they outsource that review, whereas they would just review most normal buildings in-house. So I heard this was one of your homework assignments, to watch this video on the great earthquakes of the Pacific Northwest. Did some of you watch this? Yeah, glad to hear it. I would ask what your thoughts on it were, but I don't have time, and I don't think Eli wants me to spend that much time hearing from all of you today. But I would like to say that I thought it was a really good, unbiased account of the subduction zone hazard that we have off the coast. I thought that he did a good job dispelling the myth that a large magnitude earthquake off the coast could cause a tsunami in downtown Seattle. And I thought it was also really neat that he mentioned Brian Atwater's work that identified an orphan tsunami that occurred in Japan. So the tsunami occurred in Japan, and they were able to track it back to the parent earthquake that occurred right here in the Pacific Northwest on January 26, 1700, around 9 p.m. So it's also really cool. Brian Atwater is a neighbor of mine here in Seattle, and he's an amazing detective of geologic evidence for the history of this earthquake or dating this last major earthquake, but he's also a super humble and kind individual as well. So I can't think of a better person to have done all that research. And then finally, I want to say that unfortunately, science are not able to predict when the next earthquake is going to occur. If you could, I'm sure you could make a whole lot of money doing that, but all we can do is look at the past, look at how much the faults are moving, and say, in the past it's been this frequent, but we don't know if the next big subduction zone earthquake will be next week or 200 years from now. We just can't predict that. This slide shows the 3 significant sources. We have 3 seismic sources that are most damaging to structures in the Pacific Northwest. They are crustal earthquakes, such as the Seattle Fault. The little blue dots are past earthquakes, and the black lines on this map are shallow crustal earthquakes. The Seattle Fault has the potential to be up to magnitude 7.5, has an average return period of around 500 to 1,000 years, it's believed, and last ruptured, a smaller rupture in 1833, it's thought, which was a little before the 1851 Denny Party, so they missed out on that, and then a larger rupture in the winter of 923 or 924 AD. The earthquake source that all of us know the most about probably is the Nisqually earthquake type of source, which is these deeper subduction zone earthquakes. They occur around 30 miles deep, and so by the time they get to the ground surface, the energy is dissipated, that they're not as damaging as crustal earthquakes, but they're still noticeable and can cause damage to certain structures. And then the big one that people refer to, the subduction zone earthquake, that's the source that runs along the coast from Vancouver Island all the way south to Northern California, capable of a magnitude of maybe up to 9.2, possibly 9.3, occurring every 240 to 500 years, so a lot more frequently than the Seattle Fault. And it last occurred, as I said earlier, in 1700, with about 40 of them from the geologic history in the last 10,000 years. Something else that we have interesting in Seattle is that Seattle's in a basin. Remember how I shared that the bedrock was 3 to 4 miles deep? So the bedrock could be considered either this dark blue or the light blue coloring on here. And over here on the Olympic Mountains to the west, that's up close to the ground surface. In the Cascade Mountains, it's up close to the ground surface. In Puget Sound, Lake Washington, and Seattle, it's relatively deep. And so what that basin can do, and it's been studied a fair bit. There was a workshop put on by USGS and the city of Seattle, and yours truly is right there in the middle of it. If you tell me I haven't aged a bit, I won't be offended. There was another workshop 5 years later that I also presented in. And what the basin does, this little image a coworker of mine put together, it shows that if you have a ground motion on the side of the basin, it can be relatively weak and of shorter duration. If you have a ground motion at the bottom of the basin, it can also be relatively weak and shorter duration. But if you have a site on top of the basin acts kind of like a bowl of Jell-O, that you shake the bowl of Jell-O, and as you're shaking the bowl of Jell-O, the Jell-O can shake stronger than what you're shaking the bowl. And then when you stop, the Jell-O still keeps shaking for a little while. So we have that geologically here in Seattle. Even though these are very good glacially over-consolidated soils, they're still kind of like Jell-O compared to the rock that we have below. And so we account for this in our design. So this image shows 3 cycles of the building code. The top one is the current code that buildings are being designed to, which is ASCE 7-16, meaning it was published in 2016. Before that, it was published in 2010, and before that in 2005. And the x-axis is a measure of ground shaking. It's a 1-second spectral acceleration in this case. So what you can see is that Spokane in eastern Washington is designed for a lower seismic hazard level than western Washington. They just don't get as many earthquakes, and they're farther away from the subduction zone hazard. Then as we get to Everett, Seattle, Olympia are all kind of in the same ballpark. Then we get down to Portland, it drops a little, and then once we get into California, their crustal faults rupture a lot more regularly or more frequently than ours in the Pacific Northwest. So what is interesting, though, is when we add the 2013 Basin Workshop hazard to our current building code, we actually get up there in the same range of seismic hazard as California. And when we add our 2018 basin amplification, we can be higher than some cities in California. So what we're designing to is actually a pretty large level of seismic shaking. So this is an interactive slide. My question is, which earthquake record is M9, which is M8, and which is magnitude 7? And let me just tell you what you're looking at here. The x-axis is time after the start of the recording, and the y-axis is the acceleration in terms of percent of gravity. So all of these earthquakes have the same source to site distance as well, of roughly how close the site is to where the earthquake rupture was. So the bottom one has a peak ground acceleration of 0.1 g, and then 0.26 g for the middle one, and 0.42 g for the top earthquake. So I'll give you a chance to stretch a little, and you can raise your hand if you'd like. So who thinks the bottom one is a magnitude 9 earthquake? No, one person. Who thinks the middle one's magnitude 9 earthquake? Nobody? And who thinks the blue one's the magnitude 9 earthquake? A lot of participation. So you're probably wondering why I'm asking you this question, and it's because it's a trick question, of course. So all 3 ground motions are from the same earthquake, the 2011 magnitude 9.1 Japan earthquake. We have the same hazard off of our coast. So, and they're all at about the same distance as Horizon House is to the Cascadia subduction zone. So what I want to share with you is that magnitude is not a good predictor for damage from an earthquake. Instead, there's 3 characteristics, and it's the ground motions themselves that cause the damage. So there's 3 characteristics of ground motions that cause damage from an earthquake. One is the amplitude, like how strong it's shaking. A second is the frequency content. If it's shaking super fast, it won't damage a tall building that needs kind of the slower shaking to cause the damage. And the third is the duration, just how many cycles of shaking is that earthquake contributing. So we can see the amplitude and the frequency content in this plot here. And this is getting technical again, but it's called a response spectrum. And this is what we, the geotechnical engineer, give to the structural engineer so they can design their buildings. So these three earthquake response spectrum are shown here. What you see is that actually the purple one, even though it had the lowest peak ground acceleration, which is the point here at the y-axis, it has the highest 3 to 4 second period spectral acceleration. And then what I want to point out is these three ground motions from similar source, similar distance, all of them are well below this black line. And this black line is what we're designing the horizon house to. What's also significant, if any of you are scientists or engineers, you'll notice the scale on this plot is log-log. So the difference between the line, that means that the differences between the lines are much more than they would be on a standard linear scale. So when we do our seismic hazard analysis, we essentially get a suite of response spectra. We can look at the return period and what these curves are going from a return period. The bottom blue line is a return period of 72 years to the top line being a return period of 5,000 years. So this is a measure of the strength of the shaking that we can get for a bunch of different return periods. And I'll point out that the building code is based on the 2,475 year return period. So on average, we would get an earthquake that would exceed or equal this line here every 2,500 years. And then the building code for the design earthquake it's defined as 2/3 of that level, but we're giving Amy ground motions at this highest level for her to do her structural 3D modeling with. And this is another really cool, and it shows you a lot of information if you can understand what it's doing. But this is something called the disaggregated hazard. It's a measure of where the earthquake damage or hazard is coming from with the percent contribution on the y-axis. So the bigger the bar, the bigger the percent contribution. The closest distance to the fault, or the distance from the earthquake to the site, is on this x-axis. And then the magnitude of the earthquake from 5 to 9 plus is on this axis. And so from looking at the results of our seismic hazard analysis, we can identify these really close in and 5 to 7.5 magnitude earthquakes as crustal earthquakes. These are the Nisqually earthquake, the intraslab earthquake, because it's 30 miles deep and it's of similar magnitude as the crustal earthquakes. And then we have the interface earthquakes. Those are the big subduction zone earthquakes that are far away, but they're very high magnitude. And so this changes depending on the period of our building. So for a building such as Horizon House, we're up closer to the 3-second period, and you can see that it's the crustal earthquakes and the large magnitude subduction zone earthquakes that produce the most hazard at the site.
Can you describe what is a building's period?
There's a rule of thumb. The period of a building, shorter buildings are stiffer and they have shorter periods. Taller buildings are taller and they have longer periods. And the rule of thumb is the period is approximately the number of stories divided by 10. So for a 33-story tower, one would expect the Horizon House building period to be around 3.3 seconds.
So is that 3 seconds for it to sway from one extreme to the other?
Yes. All right, so now that we know what the hazard is for the site,
I'm sorry, I can't leave it at that. How far of a distance does it sway? I don't want people to think that it's swaying like 30 feet one direction, 30 feet, all in 3 seconds.
Yeah, Amy will get into that when she does her presentation.
Okay, all right, we'll hear it later.
Yeah, that's a structural engineering question. Okay. Okay, so now that I know what this hazard is, I want to select ground motions, and I'm going to select them proportional to their percent contribution that I just determined from the disaggregated hazard plots here. So for this, the longer period Horizon House, we picked, let's see, 6 crustal records and 5 magnitude 9 type subduction zone records. And some of the records, just for those of you who are interested in this sort of thing, we picked 2 records from the 1989 World Series earthquake the Loma Prieta earthquake that caused the San Francisco Giants and Oakland A's World Series to be delayed. We picked 3 from the Tohoku earthquake, the 2011 Great Japan earthquake, that, as I said earlier, was almost a twin of the hazard that we have for the Seattle area. There's also been some research done at the University of Washington and USGS that they simulated what a magnitude 9 rupture would be from computer models. And so we've incorporated one of their models because it incorporates the local geology that we have here in the Pacific Northwest. And then I want to point out that we have scale factors, and they range from, almost all are above 1. They range from 0.85 to 2.47. So I point this out that even for these biggest earthquakes that we have out there, most of them aren't as strong as what we're designing to, so we need to scale them up. And the one that has a scale factor of less than 1 is very close to the site, and it's similar to our magnitude 9 subduction zone hazard. And so it was, because of that close sourceness is why it was stronger than what we would normally design to. So I'm going to wrap up with just some geotechnical engineering side of things. Moving away from the earthquake engineering, we do have the earth retention and shoring, and that is constructed using temporary soldier piles, legging, and tieback system, with the tiebacks and legging being installed as the excavation is underway. So there's these vertical elements, which are big steel beam soldier piles, and then as we dig out the soil, as we're excavating, they put timber legging in between the soldier piles to hold the soil in place, and then they install a tieback anchor that goes back into the soil to hold the face of it tight to the existing soil. And on this project, this is the Rainier Square Tower. They had a well point system to capture some groundwater, and we will likely also have that on our project. Again, the foundations don't go to bedrock. The foundations are large mat foundations. This is the Russell Investment Center between 1st and 2nd in downtown Seattle. It's on a large mat foundation. You can see concrete pump stations. I think there's 5 of them here with a couple concrete trucks producing concrete for each of those. And they essentially are going down into this 14-foot thick mat foundation. Our mat foundation, our building's not as heavy and as tall as this structure was, so I believe our mat foundation's 10 feet thick, but it's still a pretty impressive and sizable structure. And we do have good bearing capacity because we have glacially compressed soils, and again, it's been compressed by about 2,000 feet of ice. And then the final element is the foundation wall design. So the foundation walls essentially take over supporting the lateral load when the temporary shoring and earth retention is finished. We're designing the horizon house for some groundwater pressure, soil pressures, surcharge from the central tower, seismic soil pressure, as well as a seismic surcharge pressure from the central tower. So you'll see some of those loads in Amy's presentation as well. And that's all I have. I look forward to answering some questions afterward, but I'm going to hand it off to Amy for the structural engineering. Thank you.
Doug gave you guys a lot of information about the dirt, so let's go up into the tower and check out this building. So just as a starting point, I want to talk a little bit about the building codes. Doug commented on the ASCE 7, which is where a lot of our code information comes from, but the legal document that we are designing to is the Seattle Building Code. That is a document adopted by Seattle itself. And from that, we have material standards and design standards. So ASCE 7, which is what Doug talked about, which is design loads. We'll talk about loads in a minute. ACI 318, which is the concrete material standard. For much of this building is a concrete building. And then for some of the steel elements, AISC, the Steel Construction Manual. So these 3 books, 4 books in reality, we spend every day looking at and making sure that we're meeting all of these standards. Let's talk a little bit about engineering basics. We'll step back, and we're going to talk about vertical, so gravity loads, and then also horizontal lateral loads. So talking about gravity loading. When we're standing on this floor, you see all of our chairs and all of the things hanging from the ceiling and all of the people here. And that is all gravity loading. So what we are designing for is that loading onto a slab, and then from there transitioning to columns and walls. And that builds up over time, over all the floors, down to the foundation. So that's what the foundation soil is supporting, is all of the loads over the whole building. So what you see here is a typical floor plan for the tower floors themselves. So you'll see, this is an architectural plan, but you can see the central core in the middle. And then you'll see these little gray dots kind of around here, and those are our concrete columns. So those are the support points for the load that we're talking about. And what this is now showing is, in our analysis, what we do is we put all of the loads that we assume are going to be on the slab and analyze the slab. So that's how we design the reinforcing that's going to be in the slab, et cetera. But what this is showing is actually a deflection plot, what we would call a heat map. So you'll see the purple dots around the columns and the core. And that's where we are going to see no deflection of the slab, right? The slab is constant because there's that stiff point. Up at this north end, you'll kind of see this orange portion. And that is where we expect, based off of our analysis, to see the most deflection of the slab. What we are really looking at is to make sure that that deflection, there are code limits to it, but beyond that, even more so, that it's not something you're going to notice, right? If I think about it, my house is old, and there's a point in my house in which I put a pen down, and it will roll to the corner. That's not what we want. So we're working to do the analysis to make sure that everything for you as residents will feel flat and normal, and we're using our analysis to confirm that we're based off of the loading that we are assuming is going to be there, that will happen.
What is the maximum allowable deflection by code?
The maximum allowable deflection by code is a calculation of L, so a length, over 360. That typically averages out to an inch in a 33-foot bay. That orange portion is less than 3/4 of an inch, and that's over the full age of the building. Sorry, what we are looking at is like in 5 years, that's the deflection that we would see over the slab. So. So now moving on to, I'll say, the more interesting part, depends on who you ask, lateral loading. So the two main lateral loads that we look at on a building are wind loading and earthquake loading, which Doug talked about a little bit. Here in Seattle, while we know that the wind or the earthquake loading is in general going to be what controls the design and how we look at the building, we also are looking at the wind loading on this. So what you see in these images is actually, it's called a wind tunnel. So the red, oops, go back 1 second. The red is the Horizon House West Tower. And the gray buildings that you see around it are all of the buildings in the area. And they build a scale model of the buildings and put it inside of this contraption and push wind at it at 15-degree angles so you can see what it looks like. So just for example, this gray is not Horizon House, it's another project, but you can see what they're looking at is all of the wind loading on the building and giving us that information to make sure that we're designing to the correct loads for the worst case windstorm we can imagine here in Seattle. So just to give you guys a little idea, the solid lines are the amount of load the building is going to see in the worst windstorm ever in Seattle. And the dashed lines are what we are designing for our design earthquake. And we'll talk about design earthquake in a second, but you'll see it's about a magnitude of 5 times smaller, the wind loading to the earthquake loading. So even more so than that, right? One is how much does the building feel in a windstorm, but two is what do you feel in a windstorm? And so what you'll see here, the green dot and the green line are accepted sway. So as Eli had asked earlier, what is the period of a building? Period of a building is somewhat dependent on multiple analysis elements that we have, but is how much the building is going to move, how long it takes to go from one point to extreme to another. That extreme number changes dependent on what the force is on the building, right? It could be an inch if it's a really small force. It could be much larger. What this is looking at is how much is the building going to move in more frequent windstorms, and making sure that the building is comfortable for your occupants. So the blue and gray lines at the bottom are the analysis of the Horizon House Tower. The green are the acceptable. So you'll see we're significantly below the accepted levels, meaning that when there's a big storm, I'm thinking of the windstorm of 2006. There's a big storm, you're sitting inside your unit, you're not gonna feel uncomfortable, you're not gonna feel nauseous because the building isn't moving enough to create that problem. So moving on, we're gonna talk about earthquake performance. So what you'll see here on the top is building performance levels, and I'll talk about that in a little bit, and on the side is earthquake levels. So design earthquake, which is what Doug had noted is the 2/3 of the maximum considered earthquake, is what the building code requires that we design all buildings to. So that's that red dot that says, in a design earthquake, the building is gonna have moderate structural damage. That means most of the damage you'll see is what we call non-structural elements, partition walls, things of that sort that aren't actually part of the system holding the building up. Every building is designed for that red dot. What we are doing at Horizon House is also designing for 2 other earthquake types. A service earthquake, which is a 43-year earthquake. So this is a rare, we'll call it a rare earthquake. And the intent is that the building will be essentially undamaged. You'll never notice that you'll sit here and there will be an earthquake and you'll never notice anything. The other part of this is the maximum earthquake, which is the big earthquakes that Doug was showing. And we're designing for collapse prevention. So that means there are limitations to what the building can withstand, and we're confirming that with the maximum considered earthquake, that's what we're designing for. Can I elaborate on the? Yeah, so I can go into it a little bit more as we continue, because it may be helpful to see some of the other slides, but Doug's team has given us 22 ground motions of these very large earthquakes that are then ratioed up, and we are going through a rigorous analysis on our peer review side to confirm that we check multiple things, right? Loads on certain elements, we check how much the building moves, we check the period of the building and making sure that there's not some strange transition of the period, things of that sort under all of those earthquakes. That's above and beyond what you have to design by code, and part of that being how big the West Tower is.
Could I elaborate on that just a little bit? And correct me if I say something wrong, but it's also intended that you could exit the building after the earthquake, that the building hasn't fallen down or pancaked or something tragic, disastrous like that.
Thanks, Doug. So just to give you guys a sense, because I'm guessing many of you can raise your hand if you'd like, we're here in 2001 for Nisqually. Yep. So the top image is the ground motion for the Nisqually earthquake. This bottom motion, ground motion, is for a 2010 earthquake in Chile, which is similar to the earthquakes that we are analyzing for our earthquake design. So you'll see it's significantly larger forces that we're looking at than what we saw in Nisqually.
And the one on the bottom, how does that compare to the Cascade one in the YouTube video, and how does it compare to the Japanese?
This would be similar to, this is a little smaller, but similar to the 2011 Japan Tohoku. So Doug talked a little bit about the performance-based design. I'm just going to talk about it a little bit more. This picture here is the LA City Hall. LA City Hall is 150 feet tall. In the 50s, when seismic design was started to be codified, there was a building code height limit of 160 feet, 10 feet more than LA City Hall. that's where the number comes from. There's no science or math to it, just they wanted to be the same height or very small, similar to LA City Hall. The building code allows for a limit increase to 240 feet for buildings that meet certain requirements. That 240 feet is 1.5 times 160 feet. There's no science to it. It's just a number that somebody made up in the 50s. In the early 2000s, performance-based design was established to more safely and accurately design tall towers. So what performance-based design allows us to do is go above that 240 feet limit of the code by going through a more rigorous design process to make sure the building is safe. So as Doug noted, the peer review panel is contracted by the City of Seattle to provide a full outside review of the earthquake performance of the building. And all elements of the lateral design go through a rigorous analysis and review. This is, I think our process started a year and a half ago, and it's a back and forth between ourselves and the peer review panel, with them reviewing every calculation we have, reviewing our models, and then asking questions back to us that we have to go back and forth and discuss. Is 400?
Yeah, the question was, what is the height of the West Tower? And I believe the, well, let's just say 33.
320 feet higher than University Street.
Right.
So that's from the B1 Sunrise Terrace level, and then goes down to, I think it's about 65 feet below that is the foundation.
Right. And do we know off the top of our heads, Central Tower, North Tower, how high those are?
The Central Tower, I believe, is about 180 feet.
Okay.
If I remember correctly, plus or minus, because it's 18 stories.
Okay.
So I talked a little bit earlier, and I just want to briefly go over this of what a central core is. So that middle piece of the West Tower is, if you think of it, it's a big stick in the ground, and that is what is supporting the building during an earthquake. There are other elements that have participate in a small amount, but the majority of the work is being done by that big central core. The picture over here is from a steel tower, so that you'll see the core is actually going up ahead. This isn't quite how the construction will be at West Tower, but it gives a good sense of that sort of needle that's supporting the building. So as Doug kind of talked about with the response spectrum that he was showing on the bar graph, this is the response spectra of the building under the ASC 705, which is a code from 20 years ago, from 10, which was 15 years ago, and then ASC 716, which is what we're designing to today. So the blue line is Horizon House. The blue line is the code. Then Doug's team does a true site-specific, so specifically looking at this site and information about the geology of the site, and gives us a specific response spectrum, which is the orange, and that's what we're designing for in the design earthquake. So you'll see the two green lines. Those are the building sway of the building in the east-west direction and in the north-south direction. And that's what we use to determine how much load is the building's going to see in an earthquake. So you'll see this graph, and what I'm showing is the building under one of these ground motions that Doug has designed. So this is our actual analysis. I'm going to show it to you again, but this time I have magnified it so you can actually see the movement. So this is significantly magnified so you can see the building moving. We're talking like a magnitude of 100 in terms of what you're seeing, because as I showed you in the first picture, you can't see it moving if I didn't magnify it, but just so you can see. So we take every one of these ground motions, run the building through their ground motions, and check building movement, building drift, element loads on elements, etc. So it's a pretty significant amount of rigorous work that we're confirming that any of these earthquakes, this building will still be standing. You can walk out of it. So I talked earlier that there's the two major lateral loads that we designed to as structural engineers, the wind loading and the earthquake loading. This project itself has one other very special piece to it, and that is the soil and surcharge loading because of the central tower. So what you see here is a bird's eye view of the whole campus. And I'm now going to take a cut, which is that blue line, through the west tower and the existing central tower. So what you see here is the base of the new west tower and the slabs in the garage themselves. And then this is the new perimeter wall, so the wall that will be between the new west tower and the existing central tower. Over here in the gray is the existing central tower, and as we talked about with the gravity loading, right, all of that load is pushing down on the soil as you think about it building up over the height of the building. So that green line is the weight of the central tower pushing down on the soil. And if you think of a marshmallow and you squish it, the sides push out. And so when the sides push out, we have to have somewhere for that pressure to go. So the blue line is the side of the marshmallow pressing on the new west tower walls. So now coming to a plan of the west tower, that blue line that we showed before, that's that pressure pushing on the marshmallow. That is then going to flow through the concrete slabs and be transferred into the core walls and the perimeter basement walls. So those walls are being designed for all of that force in addition to the earthquake loading and the wind loading. And just to give you a sense of scale, the solid lines here are the earthquake loading, and the dashed lines are the earthquake loading plus the soil loading. So it's about double the load that we're bringing into the building and we're designing the west tower to support. So the central tower will remain the central tower, and the west tower will support it in the pressure on the walls. And then one last note is the foundation performance. So one of the questions that we've been asked is the concern of the building, I'll say, sliding into I-5, right? I just talked about a lot of load and making sure that the building, how does the building not slide? So if you think of it, the soil, there's a friction between the building, right, the weight of the building coming down and trying to shift against the soil that creates a friction. Doug's team has given us a number that we can design to. And the earthquake loading plus the soil loading is about a factor of 2 times less than that number that they're saying. So not going to slide into I-5. It'll still be here after everything. And just a quick, these are kind of hard to see, but the core wall, so that central spine of the building, is tied into this mat foundation with large reinforcing that comes all the way down to the bottom. And then similarly, we have columns that go around the rest of the building. Those are also tied into that mat to make sure that everything is tied together and it's going to stay. Thank you.
Great. All right, so we're going to start our questions and answers, but first, out of respect for the Let's Talk Science committee, I want to make sure that the questions that they provided us proactively, that we first address those, just to, I think that we actually addressed most of it during the presentation, but do we happen to have the questions with us?
I don't have that. I can pull it up, but.
Well, Dick, do you have the questions? Oh my gosh, well, thank you. Do you mind if I just, yeah, take a look at them? Oops. Oh. Okay. Oh, okay. All right. So the two, and thank you, Dick Cole, for tracking and which ones were not addressed. Okay, so the first question was, how recently have the earthquake resilience design requirements changed in Seattle? Does the design resilience currently planned for the new West Tower exceed the current minimum code? Please quantify the answer. Please describe the extent that cost dominated the design choices and any hard choices with respect to trade-offs that were considered. Please elaborate. So the most recent design was 2018.
Correct. So there is a new code that was just adopted by the City of Seattle, which is the Seattle Building Code of 2022, but that was adopted after we put the building in for permit. On the structural side, the design loads wouldn't change significantly between the 18 code and the 22 code. The major changes are some non-structural, non-geotechnical code changes, such as mechanical.
Okay. And so did we sacrifice any like really good design ideas, for instance, just to like maybe save money?
No.
Okay.
I mean, as Doug explained and as I explained, but the design that we're going through on this is a very rigorous design. So we are meeting or exceeding code where we can. There weren't shortcuts that we can take to get around things.
Okay. And also, okay. Please explain how the structural design is expected to behave in ground shaking conditions. Like for instance, were the flexible joints? Everything that you showed seemed to be very stiff.
Rigid. Yeah.
Rigid, I believe, is the engineer's term. Yeah, so like where, maybe you can just go into that a little bit. There's no shock absorbers, for instance, or
Correct. There are
counterweights or anything like that?
Right, there are no shock absorbers or counterweights. The flexible joints are really I briefly commented on non-structural items. So in how we detail partition walls and things of that sort, that allows for those to move. In what we're analyzing, we're looking at everything that we'll call non-flexible or rigid. All of that is included in our analysis, and we're looking at the loads and the movement of those things all together. I'd say the only joint that we have, right, is between the new West Tower and then the existing Central Tower and the existing North Tower. There are joints there because as the buildings move in earthquakes, they're not combined buildings, so they're going to move differently, and accounting for that movement between the two.
Mm-hmm. And is the massive mat slab foundation, does that move with is that expected to move with the ground?
I'll let you take that one.
Yes, the building and the foundation will move with the ground. The ground, when you think about it, there's a whole lot of mass associated with all the ground around it, and so everything that's on the ground kind of moves along with the ground. There can be some slight modification to how the ground moves due to the building there, but for the most part, things are all moving together there.
Mm. And I think I know the answer to this, but I'll let the smarter people answer. How are the columns attached to the mat slab?
Yeah, so there's rebar, so the big steel elements inside of the concrete that go, as was shown in the detail, go through into the mat, and those that come up into the columns themselves. So that's the attachment point between the two of them to have them interact together.
Nice. Okay. So let's now hear other questions, and we'll do it. Beth Barrett is not here to give the official, what does she do? She gives the official rules, but it's 4 sections. We're first going to take a question from this section in the chapel, then from the forum, then the social room, and then in the overflow, fireside lounge. I'll take this section. Lauren Charbonneau will take the middle section. And then Ashley Long, our consultant for our integrated art, who happens to be here. Great to see you. She's carrying the microphone for the social room section.
And Christie's in the Fireside Lounge.
And Christie's in the Fireside Lounge. All right, so starting with the chapel, Who here has a question? Yeah, Doris.
As a resident of the North Tower, I'm curious as to whether the same kind of analysis was done and information provided when the North Tower, before the North Tower was built. You indicated that you had done some work on that.
Sure. The North Tower was not 240 feet tall, so when the towers go above 240 feet, it requires doing the more rigorous analysis where we check the really rare earthquake and the extremely rare earthquake. And so the North Tower was constructed and designed in accordance with the standard building code.
But now that you've got us thinking, does it have a similar structural design with a robust core like our West Tower? Is that the key?
The North Tower does have a core,
Okay.
and it would be a robust core. It is a core building. It actually has two cores because of the L-shaped version or L-shaped nature of the building.
That's the central tower.
The North Tower, because of where the Parkview Bridge is, that has a
Oh,
core
right,
piece in
right,
that
right.
portion too.
Okay, yes.
But it is a similar structural design in terms of the lateral element that's supporting the building for the North Tower.
Oh, okay.
John?
When you consider your 10-foot thick mat slab, that's the one at the base. I presume that's just totally integrated with or shoved full of rebar, interacting all the way through it. Can you tell me what's the thickness of that stuff and how frequent the rebar sits? It isn't just a 10-foot thick of poured concrete by itself.
That's correct. So the mat itself, I'll say it's 10 feet thick directly under the core. So under the tower itself, as we go to the north, it gets a little bit thinner because of the loads being smaller on those columns. But everywhere in that mat, there is reinforcing at 12 inches on center, both at the top and bottom of the mat. Directly under the core, where we've got heavier loads, both from the gravity loading and then also as we talk about the building, I'll say rocking in an earthquake or wind, and we have upwards of 5 layers in each direction of bars at 12 inches on center or 6 inches on center. So, if you think of that, that's what, like 10 inches of steel kind of depth through that section. And then in addition to that, we have vertical bars, specifically in the core and tower area to make sure I'll say the concrete doesn't crush under a vertical loading.
And these rebars that are going through there, I can imagine 1/2 inch, 2 inch, 1 inch, 3 inch. What size bars are they?
Yeah, so in general, they're typically 1.5 inch diameter bars.
Thank you.
And in general, like, how do we associate the foundation, the mat foundation, in terms of mass? How does that relate to everything above it? Is it like maybe 20% of the total weight, or?
I don't know the number directly off the top of my head, but it's about 20%. It's a pretty significant amount of the mass of concrete in the building, because if you think of it, it's 10 feet, and most of our typical slabs are 8-inch slabs. So it builds up quite quickly, but it's 20 to 25%.
Is there a staircase system planned? How many, and how is that affected as far as reinforcement is concerned?
How many staircases? How many stairwells? We have 2
and
significant.
how does that affect the whole structure?
We have 2 primary stairwells in the core, and then an additional 2 stairwells in the elsewhere in the podium, but 2 for the tower that go up the entire 33 stories. For anybody who wants to run it with Lauren.
To answer your question about the reinforcing side of it, those stairs are designed to, they're designed by another engineer, and they're designed with a slip joint pretty much to account for we tell them how much the building is going to move under different events, and they have to design for that movement and drift in their stair calculations.
Sorry. And about the elevators, how many and how is that going to be?
We have six
And how does
Six
that
elevators.
affect, since they have a sway of their own?
Yeah. Four elevators in the core, plus another 2 shuttle elevators that do not go up to the 33rd floor, but 4 in the core. And the question was, how are they expected to perform with the sway?
Yeah, so similar to the stairs, we provide the elevator manufacturer with direct information to how much the building is expected to move under different events for them to account in this way of their elevators.
Are there any questions in the Fireside Lounge?
Yes, we do have one. Are you ready?
Yes.
How thick is the concrete base, and how much does it weigh?
So it's, I thought it was at 13 feet at its thickest.
It's 10 feet at its thickest,
Okay, 10 feet at its thickest.
and then it tapers up to 4 feet thick where we have lighter loading, so out, I'll say to the north side, where we only have the podium levels. And as I noted, I think it's about 20 to 25% of the total weight of the building.
I see. And would this be a better building if it were built with steel?
It's a hard question. No. I do a lot of concrete buildings, though. No, it would not be a better building if it were built of steel. There's pros and cons to both the concrete and the steel options. In, I'll say, residential buildings, one of the pros of doing a concrete building like we're doing is that it allows for very thin sections on the slabs. So the typical tower slab that I showed earlier is 8 inches thick. If we were to design that in steel, that would be about 2.5 feet of depth for all the steel framing and the floor system itself. So if you think about that, what is a 10-foot floor-to-floor now becomes smaller than 10 feet, and it starts to take away from things. So typically on residential, doing concrete allows for larger floor-to-floor, more nicer units, etc. On the lateral side, most steel buildings would still have a concrete core, so the lateral really doesn't change. The steel is slightly lighter than the concrete, and that's about the major pro there.
Okay.
There are 2 buildings that I think of. One is the apartment building just beyond here. What is it called? Cielo. And then at Swedish, they're also building a new tower. What did you learn from those 2 buildings that are in the design?
Are we familiar with the structural design of Cielo? Was it a steel reinforced concrete building?
I assume it was a reinforced concrete tower.
Mm-hmm. And how does that relate to the West Tower?
It would be the same construction type as the West Tower,
Okay.
I believe.
All right. I would imagine that there wouldn't be too many things different since both projects fall under the same building code, and they're both the same construction type. They are both about the same size and height.
The one you're speaking of may actually be one cycle behind because of how the code worked. It may actually be the previous 2015.
2015
Yep.
code. Okay.
So-
And then the other building was the new Swedish building that's being built right now, just on the east side of Boren. Yeah. What do you have to say about that? Are you familiar?
I'm not familiar with the project itself, but again, I think dependent on when the building went in, it probably is one cycle behind Horizon House in terms of the building. Just because it's current, the building code,
Right.
when it flips over, when they actually put the building in to design into the city.
When it received its permits, when
received
they
its
were
permit,
reviewing
yep.
it for permit. Right.
Yeah.
Nice. Good questions.
I would just add that Amy and I have multiple projects underway at any given time, and we've done a lot of projects in the last 5 to 10 years. So the learnings we get from each of those projects, we add to the next project we're involved in.
In the, I think it was a 2010 earthquake in Chile, it was 8.8 or so. There was, I understand from an architecture friend that the building codes in Chile were similar to those of Seattle, and yet there were failures. Buildings collide and so on. Can you comment on the risks should we experience such an earthquake?
I'm going to pass this. I'm going to take the microphone back to my colleague at the back, David Fields, because he has the answer to the question. Oh, he's.
Hello, David Fields. When Amy says me and my team, I'm part of her team, I'm part of Amy's team helping to design the building. So the Chile earthquake, well, let me step back. The building codes that Amy showed at the beginning, the 3 books that we use to design our buildings in the United States, one is just about concrete buildings. Horizon House will be a concrete building. That code is used in about 100 countries around the world because they recognize the high level of expertise of the United States designers and academics. And they don't have the resources to create their own building codes. Now, some of those countries use it in very peculiar and selective ways. What Chile did is they used our building code, our concrete code, and they excerpt a specific piece because they thought it would cost too much. And it has to do with concrete walls and the reinforcement, the rebar inside of it. We see lots of vertical rebar in walls, but they also have to wrap it all up and put extra rebar hoops and things around it. And that's costly and difficult to build, and they decided to cut that out of their code. And that's largely what they see as the failures and the skinny ends of shear walls during that earthquake.
Yeah. Good question, good answer, right? Ashley? Jean, yeah.
Yes. I read particularly in RMI and other organizations that are very interested in saving the atmosphere from carbon, that there are lots of steps forward in ways in which concrete can be made without as much expending of carbon or with no carbon that will be expelled to the wall. Is any of that at the level to be used in the size of a building here?
So I think that might be a question for Andersen,
Okay,
since
Andersen.
they're procuring it. So, obviously, Amy, she specifies the the performance requirements, but Andersen is procuring the concrete. So I think what Jean is asking is carbon sequestration words, buzzwords, something.
Yeah, I can answer that one. So yeah, there is options for low carbon concrete. Typically what that does is it creates the concrete to strengthen slower over time. This type of building with PTs and so forth. Yeah, post-tension cables in there. We need it to get the strength right away so that we can stress that and continue up the building. Otherwise it could, make the structure of the project be 3 to 4 times longer. So it's not a good option for this project, no. And Amy, I don't know if you have any more technical stuff to add, but that's what I got.
Yeah, I mean, what Chris
To be developed.
Yeah, what Chris noted is true. We do work directly with Andersen to make sure that what we're specifying, if there's any opportunities to help with the carbon reduction, that we can do it with the understanding of schedule and workability of the concrete itself.
Yeah, and delaying the project as much as what would be needed, is just not feasible. And this is Chris Peterson with Superintendent of Andersen Construction. Yeah.
Are there any questions in the fireside lounge?
Yes. Yes. Are there any other buildings anywhere in the world using the combination of elements in support structure that you're planning for this building which have been subjected to weather or other kinds of stress?
Yes. There are lots of buildings. The construction type and combination of construction type that we're talking about is a pretty typical tower that you will see from Miami to LA to New York to Seattle. So all different types of weather conditions, lateral conditions, etc.
Well, like Tokyo, or what's the name of the city in Japan with the earthquake?
Tohaku.
Tohaku. Are there similar sized designed buildings in
Tohaku.
Tohaku?
Tohaku.
Tohaku, as the West Tower?
I don't know in Tohaku specifically, but there are building types like this in LA, right, which sees earthquakes similar.
Okay, so similar earthquakes. The problem with LA, though, is that I think the question is, this is a very temperate climate. We get a lot of rain. And so something, I guess, similar to us that's represented elsewhere has the proof of concept. We're not the guinea pigs.
We are not the guinea pigs. There are thousands of buildings like this. And I mean, even just here in Seattle, this is a pretty common building type when you're talking about residential type towers and not office towers.
But they have also endured earthquakes and survived just fine.
Yep, correct.
Performed just fine. Okay. All right. Anybody here? Yes.
I have a question about the clay level under the building. My understanding, and I may be totally wrong on this, but is that during an earthquake, clay liquefies. The jiggling of it makes it liquefy. And have you taken that into consideration, or is the compacted clay really not going to do that?
Good question. I meant to speak to liquefaction during my presentation, but it was an oversight. So liquefaction is primarily occurs in loose sands, not clays, and it's sands that are below the water table, so they have to be saturated. And so when you have a loose sand, the earthquake shakes, they lose the interparticle friction, and it becomes almost like quicksand. And so that is not a phenomenon that's seen in clays. The water can't move around inside of the clay because it's very fine-grained, and so it's not a problem for this type of material. But excellent question.
Does anybody know if the folks who have made a commitment to the West Tower, were they invited to this presentation?
Lauren, no.
That's unfortunate.
I agree.
Is this being taped?
It is.
Okay,
It is.
So they'll have access to it.
Yeah. And we can always do something like this again, right? It's a lot of fun.
Can I ask a question?
Yes.
I'll get you on the next round. Okay.
Ashley?
Okay.
I don't have a question, but I wanted to pass on an experience I had since we're dealing with structural issues. The day after the Twin Towers in New York were knocked down by the airplanes, I happened to go to a Seattle Rotary meeting and landed at a table where you walk in and you just sit with whoever. One of the guys at the table I was at was the son of Skilling or Magnuson, whichever one of them was the main designer on those two buildings. And the upshot of the discussions with him was, everybody's worried about earthquake, but wind is much more threatening. And of course, that's a 105-story building, unlike our low buildings here. He said that, and this is what astounded everybody at the table, if only one of the planes had taken down one of the towers, the other one would have had to have been removed anyway. You couldn't possibly occupy it. because in the structural design of twin buildings like that, the sides toward where they're next to of the twins are next to each other have much less steel and structural support. And if the other building is gone, all of a sudden the insulation for that weakness side is gone, and you couldn't occupy the building. They would have had to tear it down. That's what we were all astounded, but he said that's the way it goes. I thought you'd all like to know that one.
Yeah, interesting fact. Yeah.
Any questions in the fireside lounge?
All right, back to the chapel. Anyone? Yeah.
Sounds like a great design. However, the issue will be in the construction. Could you give us the surety of inspections so that the issue of the quality of concrete and the quality of steel and its construction will meet the standards that have been designed for?
Yeah, what kind of quality control is there during a construction project, Chris?
Oh, come on, just trust us, right? No, so not only do we as Andersen Construction have our own quality plan where our staff goes through, checks everything that's done by every subcontractor, but also for major structural elements like that, there's third-party inspectors who will be on site full-time who do not work for us, aren't affiliated with us.
We hire them directly. The name is Finet. Finet is our commissioning agent for special inspections. So they'll be doing concrete slump tests and
Yeah, every piece of it, they witness the work, they check it before it goes in. And then there also is some city inspector for some of the mild stuff as well, but all the major structure is that third-party engineer or third-party test agency that checks, triple checks what we're doing. Yep.
Good question. Sam.
So,
Wait, Eli. Sam can go next. I'll get him on the next round.
so I have another question. So, since it was mentioned over here, talking about the elevator shafts and the function of elevator shafts, I was going to bring this up to a different conversation, but I think the opportunity is now. One of the things that senior management of Horizon House came to the conclusion of was that the elevators that we had were not the most expensive elevators we could have purchased. But if we'd have bought better elevators, we wouldn't have had all the problems we had later on. Are we getting the very best possible elevators so that we'll be able to skip some of the problems we've had with our current elevators?
Yes, we're definitely making sure that we're specifying. We've been going back and forth between either is it Otis or ThyssenKrupp? Okay, so yeah, ThyssenKrupp elevators, very reputable. And a third party, Lynch Bates. Lynch Bates is our third party consultant who's helped guiding our owners, Horizon House's project requirements. Yeah. Let's see. Right.
I used to live in Chicago in a 24-story building. We lived on the 12th floor. And you were talking about wind shear. And in Chicago, at least in our building, we used to have quite a bit of wind shear, even on the 12th floor. In fact, in our living room, we had a chandelier, and in a windstorm, it looked like the chandelier was moving about almost 6 inches. It wasn't the chandelier that was moving, it was the building that was moving. The chandelier was standing still. Will we have any of that sort of thing happening?
So as I described about the wind tunnel test that we had performed on the project, the wind loading under a major storm is small in comparison to the earthquake loading. But in addition to that, right, we also are looking at, I'll say, a smaller wind return period is a weird thing to say, that's very technical, but right, the windstorm that happens every few years or every year, and making sure that the building isn't moving so much that you'll notice the chandelier moving in your unit, sort of thing. So. Yeah.
Are there any questions in the fireside lounge?
No questions out here.
Okay.
Anybody?
It's currently 5, so we can do one more round, and then we'll end questions.
Nice. Anybody in the chapel?
Well, thank you for this presentation. I'm curious, the Smith Tower was built in 1914, which is 110 some years ago. How is it that building has structurally been so successful given the earthquakes that we've had in Seattle and the highly sophisticated design that you all are preparing for the West Tower? What do you know about the difference?
So I'll say that the part of the reason that the Smith Tower has done so well is redundancy, right? The structural system is much more redundant, meaning there's a lot more material to do the same as what we're doing at the West Tower. I don't know the exact structural lateral system, but I think it's something like a core wall around the exterior of the Smith Tower that has punched openings. So if you think of that entire exterior is the spine that's supporting the building. As we have moved through history, the design codes have gotten there more load that we're looking at, but it's also accounting for trying to be more efficient and still stay as safe, if not safer, than buildings from 1914 and 1920. That sort of in the 50s when we started really building codes, that was the point of it, was to make sure that we were making the safest buildings based off of the science we understood, but also accounting for not having 3 times more concrete on the building, sort of thing.
Mm-hmm.
Sure. It's still built, it's still standing, right?
We have one question right here.
I want to thank you both for a really very good explanation. And I think you put to bed the question of design margins and safety. And that will make us all sleep a little bit better. Thank you.
Ashley, we'll get your question.
When I was visiting different communities to decide where to live, one place took me to show me the rooms, and in the room was a pillar, and they said, this is the earthquake prevention, and it had a little space around the pillar, and they said this is to allow it to move. When we see our new building and we go into it, will we see any structures that are part of this earthquake, this excellent design, or will they all be embedded outside of view?
They will all be embedded outside of view, except for a handful of columns that you will see, but you won't, the columns are interconnected with the slab, so you're not going to see a joint around the column to allow for movement.
Okay. Any questions in the fireside lounge? Last chance. I think we're good.
Thank you.
So wait, one more. Great, thank you all so much for attending, and for Doug and Amy for your presentation. You too, Chris, you're okay.